Hi, welcome to the lecture on Chapter 2, Recursion. Some of you may or may not have covered recursion in your advanced C++ or Java classes last semester. So we'll kind of cover the highlights of it, kind of talk about the differences between iteration and recursion. How do I solve problems? Then we'll talk about, once I understand the difference between those two types, and most of the programming you've done so far probably has been in the iteration department. So if you're programming things, it's probably what? I'm writing a loop, I'm doing things over and over and over and over again, or I'm going to call the function over and over and over again. So we'll talk about the differences. Then we'll talk about how to design a recursion algorithm, a recursive algorithm. We'll determine when recursion is a good solution or not. And then we'll kind of look at some sample functions. Now, what we're going to use, a factorial. Some of you remember math, where a factorial is what? If I got a 4 factorial, it's what? 1 times 2 times 3 times 4. And sum those up together. But for this case study, I want to use it as a case for discussing what recursion is and to define the concept and both go through the iterative and the recursive solution for that algorithm. Now, what is iterative? Well, basically it means it involves only the algorithm and parameters are called, but you don't call the algorithm itself. So I don't have the algorithm calling the algorithm, the program calling the program itself over and over again. But recursive it's a repetitive process, but the algorithm calls itself. And then we'll talk about a little bit about solution here in a little bit. So here's how, in the textbook, we're going to use to define algorithms. So in this case, I'm looking at a factorial, and you got two different parts to this. Let me see if I can get my mouse to come back. This part here is called the base case. It ends up actually having a solution, and then the remainder of it is the rest of the algorithm. So I've got, in this case we said factorial n, I got n times n minus 1. So it'd be, let's say n is 4. It'd be 4 times 3 times 2 times 1 to give you the solution. So it's calling itself over and over and over again. So I'm calling factorial n minus 1, calling factorial n minus 2, and so on. So now, this is how I would do it recursively. I would loop through and go 1, 2, 3, changing maybe I in your loop multiple times. Now, if I was doing it recursively, here I've got factorial n, so I still got my base case, which gives me a solution, but now I've got what was the number times. Now I'm going to call that same routine a second time, but I'm passing a different parameter to it. We'll go into a little bit why I would pass a different parameter to it here in a second. So what happens on a recursive algorithm? So if I've got factorial 3, so according to our formula here, factorial 3, I've got 3 times factorial n minus 3, so 3 minus 2, so ends up being factorial 2. So I've got factorial 3, so I got 3 times 3 minus 1 is 2, and call it. Now, what happens when it gets to this case? I got 2 times calling factorial 1. Calls factorial 1, and again, I get down. At some point, I've got to reach that base case where I actually have a physical solution. And once I've got this, and we're comfortable with, hopefully by now, that when you make a function call, when that function completes, what happens? It returns the value right after, returns like one step right after its call, right? So in this case, I got a solution. So my base case went all the way down. It solved the solution. Now I can replace that value. I got 1 times 1 is 1, replace it, and my work is, so I'm calling it on the way down, keeping going down until I get a base case, and now I keep returning values, return a 1, return a 1, return a 2, and multiply it, and eventually it'll go all the way to the top and get the cause, what the solution is for the factorial. Now, as you can tell, it was kind of a two-way journey. On the way down, I'm decomposing the problem into smaller and smaller solutions, or smaller and smaller problems to solve from the top to the bottom. But once I got to the bottom, I'm going to solve the problem, giving you the final answer all the way up from the bottom to the top. So basically, recursion is a repetitive process in which the algorithm calls itself. So we're kind of taking advantage of knowing what a computer does. So here's kind of what would happen if I was going to write an algorithm. Now remember, in chapter 1 we talked about what the definition, how we want algorithms to be written in pseudocode. And I'll give most of our examples in pseudocode. Some of them may go with the source code again, but for the most part, I want us to think pseudocode problem solving. So here you've got a title. Of course, you can make sure the title is interesting, or at least explanatory, and a description as to what happens. So it calculates a factorial of a number using a loop. So it's going to be iteration, not recursively. I got a precondition, where n is the number that's raised factorially, and postcondition says, hey, I'm actually going to return that final value, that n factorial. So what am I doing? I got to first initialize my variable. I've got to set the variable factor n to some number. In this case, I'm initializing it to 1. Now I'm going to loop through the number I, so that's 1 less than or equal to 1, and I'm going to keep going through. And I'm going to assign factorial n to n minus 1, increment I, and keep looping through this. And once I finish the loop n number of times, I'm going to then return, whoops, lost my cursor. I'm going to return what that value was. So I started out value 1. I've multiplied 1 times the number I, which it started out being 1. So I got 1 times 1 equals 1. Increment I to 2. Is it greater than or equal to n? Well, remember what n was. N was past what the factorial I wanted to. So I'm going to keep looping through that until I go through this. So in our case of 3, you're going to go through this, 4 times? So this is the algorithm, how it is. So you get a sample. You pay attention to some basic algorithm naming conventions. Remember our numbering conventions. I don't need, when I start getting indentations in the code, I don't need to put 3.1, 3.2. I can just put 1 and 2, and I'll be able to determine that loop. Now, how would I do that recursively? Okay, I still have factorial, recursive factorial, same thing, but now my definition has changed. I got my pre and post conditions are identical. Now, here, it says here, I've got 2 different conditions. I've got a condition where it says, hey, if it equals 0, I'm just returning the value. So if you remember up here when we talk about the factorial, my base case says, hey, that solves the problem. So that if it equals 0, that's my base case, just return. If it's not my base case, now I'm going to return by calling it with n minus 1. So I'm going to return n, and then I'm going to call. So you can tell the code itself is fairly straightforward. It's going to keep calling itself over and over again until what? Until n equals 0 and I return 1. And then I'm going to pop that information back. As we saw in the diagram back here, I'm going to call it, get down to once it solves that case, then I'm going to keep popping and inserting the solution for each one of the cases that I called. Now, this is kind of the pictorial of how that diagrams being called in case we start out with factorial recursive 3. So what am I going to do? My first step is I'm going to call it n minus 1, call it a 2. It's not equal to 0, so I got to call it with n minus 1 as a 1. It's still not equal to 0, so I got to call n minus 1. Now it's equal to 0, so I'm going to return a 1. So I return a 1 for this value, do n minus that, return that value, so I'm going to return a 1 because it's what? N is 1 times 1 is 1, so I'm returning a 1. Now I got n is 2 times 1 gets past a 2. Well, now I've got, here is n is 3 times 2 gives me a 6, and I'm passing up the value 6, and then I go ahead and print the number 6. So you can kind of tell that going down, I'm calling each one, passing a different value, and once I get to that base case that actually can solve the problem, now I return that value over and over again. So the question is, how do I design this? How do I design a recursive algorithm? Now, so we'll talk about a little bit about the methodology. We'll talk about some of the limitations and maybe some examples of how it's implemented. So I mentioned before we had a couple of elements to it. Every recursive algorithm has two elements, a base case and a general case. Base case is the one that solves the problem. Every recursive algorithm must have a base case. The second is the general case, and that's the rest of the algorithm. So what happens if this one doesn't solve it? So in our recursion algorithm, so here, so using our factorial recursive algorithm, you see we've got two cases. I got the base case, which actually solves the problem, gives me a solution, and the general case. So this n times factorial n minus 1 is the general case. Now, we got to keep in mind that you've got to, when you're designing your base, your recursive algorithm, at some point your general case better be finding a way to get to your base case. It has to reduce or changes the size of the problem to the point where it leads towards a base case so you can actually have a solution. Otherwise, what do you get? An infinite loop potentially in your code. So rules for designing recursion algorithm: one, you got to determine what the base case is. What problem am I trying to solve? And then I got to determine what the general case is. How am I going to subcategorize? How am I going to break this problem down into smaller pieces and then combine the two together into an algorithm? Now, you got to be careful about the logic, because each call must reduce the size of the problem and move towards that base case. And of course, the base case must terminate. It can't just go on forever. It's got to terminate also. It's got to come back with a final solution that doesn't recall another call. So we wouldn't be trying to have a base case that it calls factorial here. So it's got to be a point where I've got a final solution that I can't call factorial again. So you got to first what your base case is. So design what that base case is. Determine the general case, what's going to keep reducing this problem down to a small set. Pay attention to the logic, because you want to make sure that the logic of your recursive algorithm actually reduces the size of the problem, moving towards that base case. And of course, the base case can't call the function itself. Now, there are some limitations. Now, a good way to see if recursion is not to be used, if any of these questions is yes, then you go ahead and use recursion. So do not use recursion if I get, I'll have to double check that. Is the algorithm or data structure naturally suited for recursion? Yes or no? Is the recursive solution shorter and more understandable than an iterative solution? Yes or no? And does recursive solution run within acceptable time and space limitation? I mean, you're trying to do this to run faster, but if you've got a time or a disk space or memory configuration, so does this run within it? So if I answer yes to any one of these, it would be a good case to use recursion. Now, when it comes to efficiency, we talked about in chapter 1, efficiency of an algorithm. If the solution doesn't give you at least a logarithmic efficiency, you probably don't want to use it. You want to stick with the iterative. So just some basic questions you can ask to kind of help you through making decide whether I'm going to do it or not. Now, let's look at some of these. Let's do a case like, let's reverse the keyboard input example. Base case, what is the last case? If I'm typing a set of characters, when do I know my last case is? Well, the base case is when the last character has been read. The last piece of data has been read. What's a general case? I want to read the next piece. So until I have reached kind of like that end of line, or if you're typing on a keyboard, until you hit that carriage return, I'm still in that, that next, in that general case. Now, the question is when you're forming these two, so I got my general case, got my best case, but since I want to print an answer, when do I want to print? Do I want to print as I read each, or do I want to print after the last piece of data is read? So as you're formulating that solution, you want to think through this type of question. So I first decide what's my base case. What's going to determine I've got a final solution? That's by that last bit of data read. So that's when I hit my fifth character, when I'm typing the fifth one, hit a carriage return. The general case is, what did I do for characters 1 through 5? And what do I do? And then the question is, how do I print it? So let's look at one possible solution here. So I've got an algorithm title, description, and it is being passed data, in this case, whatever I type at the keyboard, and I'm going to print what I type in reverse order. There is no precondition, and the postcondition is I'm printing all the data entered in reverse order. So I start out with looking at, if I'm at the end of the input, just return. Now, keep in mind when we're talking about algorithms here, or at least as far as pseudocode is concerned, you got an if and then end if. So you got to put those two conditions together. You do the same thing on a loop. But right now, so you got an if, end of input, yes or no. It's no, I'm going to return if it's true. If I'm at the end of it, so if I hit carriage return, I'm going to return. If not, if I'm not at the end of the line, I'm going to read the data, read whatever first character was typed in, and then I'm going to call the routine again. So I'm going to call print reverse again, and then pass whatever data is left. So now I'm going to read the data. So now you look at, what did I do? We printed after we've made all the calls. So there is no calls. We've decided that I want to print at the end of my routine, or at the end of the function. So what happens when I get to the end of the routine, I'm going to return, but I'm going to return after I print the data. So you can kind of tell that it's fairly simplistic. So what am I here? I've got a base case. Here's my base case. And then what happens with the rest of my routine? I'm going to continue reading data and then calling it in. Now, what happens here? My read data says, give me that next character. So I'm reducing the character size. So I'm reducing that general condition and making sure that I'm moving towards that base case. Just to give you a rough idea, we type in 6, 20, 14, and 15. So I call it with data 6. It says, hey, is it the end of return? Is it a carriage return? The answer is no. So this is not true. So I go down here, read data. Well, it's okay. That reads data ends up being 6, but now I call that again and then read the character 6. Goes down here, reads data. It says not the end. Read data. That gives me a 20. Goes down here, read data. It's 14. Read data. It's 5. And eventually I got, hey, new line. I'm returning. Now I return to where I left off. I print 5. I print 14, print 20, print 6. So enter the data 6, 20, 14, 5. It's printed 5, 14, 20, 6. Let's look at 4 recursive programs that definitely have some historical value, at least as far as computer science is concerned. Of course, we understand greatest common denominator, but Fibonacci prefix to postfix, you're probably going to use that when we get more into graph and tree traversals. And then the towers of Hanoi, and I'll explain that in a little bit. So these are 4 common opportunities to have recursion used to the benefit of both understanding of the problem and speed and accuracy. So let's look at greatest common denominator. Here, what have I got? Greatest common denominator, A and B. So I got A and B, my general case, they end up being, turns out to be 0. Now, here I'm going to call like greatest common denominator variable B. And now this is the modular function. So keep that in mind. That's what you're going to do. So now what are we going to do as far as the algorithm is concerned? It calculates a greatest common denominator, greatest common divisor, I'm sorry. A and B are positive integers, and what's returned is the greatest common divisor. So if B equals 0, return A. If A equals 0, return B, because that means they're identical. And if not, I'm going to call greatest common denominator again, pass B, and then pass A, the modular B. So basically, what is that solution? So it's fairly straightforward, fairly simplistic. You can tell that, the values changed. It's got a couple of base cases. Now, it does have multiple base cases because I've got multiple values that I'm passing, but at least it gives me some solution here. Let's look at Fibonacci. Fibonacci is what? I've got a couple of cases. What happens? And basically all I'm doing is adding together, 4 plus 3 plus 2 plus 1 gives me the Fibonacci number of, in this case, example 4. So I got a base case, 0 and 1, and then calling the function 3 different times, or at least as many times as necessary. So just to give you a rough idea what happens with the number of calls are made with Fibonacci. So if you put in Fibonacci just 1, I make 1 call. Why only 1 call? Because it's number 1, it's a base case, I solve the problem. If it's 2, I've got to make 3 calls. And you can tell it kind of keeps growing. It doesn't take long to get a very large number of calls, so it becomes fairly simplistic. Now, when we're talking about graphs, there are 3 different arithmetic formulas or expressions that can be used. I can have infix, which is probably what we're used to, A plus B. There is postfix where I get A, B, and then what operation am I going to perform on those two? Or there's prefix where I say, here, I want to add A and B. 3 different ways, all come up with the same number, but just 3 different formulas or expressions on how to get that addition done. Some of you got a calculator that says, hey, I got to tell what my operation is and then what are my 2 variables. Most of our calculators probably work on A plus B equals whatever number you type in. So 3 different formats. And what I want to do is I want to convert the sequence I put in and come up with a solution. So if I took a calculation like, because what am I doing? I'm doing converting prefix to postfix. So I'm going to take this prefix with the operation out front with all the variables in the back, and I'm going to convert it to variables up front, operations in the back. So if I have an example of I've got a subtraction, an addition, a multiplication of A, B, and C, a division of E and F. So what do I got? I got to break this down a little bit and say, hey, here's my first character, so what are my choices? So, well, here's my first one, so I got to break. Here's my next operation. Here's my second one. So I've got plus multiplication A, B, and C minus division E and F. I break this down again. Here's my addition, so it goes down here. I got multiplication A and B. Last one is C. And in E and F, you pretty much get, here's my division, here are my 2 variables that you're going through. So you got to keep breaking these down. So I'm decomposing this because what do I have to do? I've got to take, because what is prefix? Prefix says operations, 2 variables. So I got operation, and then these are my 2 variables, plus ABC divided EF, and you keep breaking it down till you get down to that lowest common denominator, that lowest piece that can't be subdivided or decomposed any further. Now, how would I convert that? Now, how would I write an algorithm to take this string and convert it to PostScript? Now, because what would the postfix conversion be? Because you have to make sure all the operations are on the back side of this. So here we've got, here's your algorithm. What's my number in? And I'm going to return my postfix. So converting prefix string to a postfix string. Now, it's got to be a valid prefix, and then I'm going to give you return a reference to a converted expression. Those are the 2 inputs. The output's going to be the converted expression. So one I'm going to double check is the length of what's being processed. Is it equal to 1? Otherwise, the base character, I've only got 1 character. I can't break it down any further. That's what I'm looking for. Once I've done that, I'm going to set my postfix. What came in is going to get assigned to postfix. So prefix in gets set to postfix, and that's going to return. This is my base case. I can't go any further, can't return anything smaller. So now if it's not an operand, it must be an operator. So what happens if I got to set the operator to the first character of the prefix? So, because what we said, the operator is my first character, right? So set the operator to the first character of the prefix, and then find the first expression. Now I got to look at how do I know the length, what is my length of that expression that I'm trying to operate on? So in this case, we're having a routine called length of expression. So I'm going to do find length of expression and pass the number in less 1 and assign it to the length. And I want to double check, is that length, so I'm going to take it a substring of that variable, look at two different values, set it to temp. I want to take a prefix, and then I'll go, ooh, I'm calling the routine again. So here's my recursive call. I want to change the length again. I'm going to call it again. And then what's going to happen at the very end, I'm going to add them all together and return. Let's look at one more. How about if I just say, what about the length of a prefix expression? So you had this prefix expression. What's the length of it? So it recursively determines the length of a prefix expression. So one, I've got an expression that's in prefix, a valid prefix. Now, normally if you're writing a routine, what would you do? You'd probably write an error code to check the format of it, check the validity of the structure. But being just an algorithm, we're going to make some assumptions that as a programmer, you would then say, oh, how do I know it's a valid routine? Now, in some cases, you're going to say, okay, what is the first case? First character, if the first character is an operator. So guess what? In the general case, that first character has to be an operator because it isn't broken down any finer. So of course, now I got to find that length of that expression. So I've got, set length 1 to whatever the length of that expression plus 1. And length 2 is the expression plus 1 plus that length 2. So I'm calling myself. I'm going to call the routine. Here's my recursive call in that general case. Otherwise, here's my base case. If those are equal to 0, I'm done. And then I can return the value. So I'm going to set it to 0. And of course, then return, go on. So you can kind of see, get a general case, base case, but this example also shows you I don't have to have the base case to be my first part of my algorithm. Here you got your general case followed by your base case. But in either case, that base case has got to shorten the solution or the problem set, and then the general case then calls the function again and keep repeating. Now, the last one I think we're going to look at is the Towers of Hanoi. It's been around a while. It's an ancient story that a bunch of monks were going to try to predict the end of the world, and all they had was 3 needles, and with the first one having 64 disks of decreasing size. But they only moved like 1 disk to another needle once an hour, once a day. So the rules were I could only move 1 disk at a time, and a larger disk, but it's never being stacked on a smaller one. So it always has to be largest to smallest. And then only one auxiliary needle could be used for intermediate storage. So seems like it's fairly simple. But so you start out with something like this. What I've got, here's my source. I want this sequence to be duplicated. I want my sequence from the source to be duplicated at the destination, but I got to make sure is I can take 1 off at a time. This auxiliary can only be used, what did it say? I can use 1 and only 1 auxiliary needed for intermediate storage. So if I'm just using it as a holding spot, I can only use it 1, just short time. So here, let's look at a 2-disk solution, A, B, and C. So I take B off. So I got A and B. Now remember the rule, I can't place a larger on top of a smaller one. So A goes to C, and then B gets put onto C. I only use 1 disk as an intermediary, and I can't have a larger one on top of a smaller one. So you can kind of see that the progression here as far as how to get a 2-disk solution. Kind of look at a 3. Let's see, do I have a graphic on a 3? Yeah. So here's your routine for 3. Let me show you the picture first. I start with 3. What can I do? Step 1, I can take that off and move it to C, because I can use one of the intermediary piece. Keep in mind, what am I trying to do? I'm trying to move from source to destination, but I can't have smaller and larger. So I got to get the top one to C, second one to B, and now I can do, C on top of B, which then frees up A, which then means I can move A to C, which then means now I've got to take the top one, B, since I still got one spindle left, I can move it off, move B on to C, and then move that to A. So using only one spindle, keeping track of I can use only one intermediate storage, and I can't have any stacking larger on top of smaller. Well, this algorithm suits itself very well for a recursive algorithm. So you're going to recursively move disks from source to destination. The number of disks is the number of disks to be moved. And then the source and destination auxiliary towers are given. So since you only have 3 of them, that you already know. And then once it's done, you're going to print the steps for the moves. So we're going to start off with, I'm going to do a print, give me my title, and basically say how many disks did I start with, what's my source, what's my destination. So I'm going to print the input that we were given. Now, if the number of disks is 1, I'm done. There's only one more disk to move. I can just print the move. Now remember this. Now here's my base case. I've got a final solution. I can't break it down any further. And now here's my general case. So I'll do the number of disks. Here's my source, auxiliary, destination, and step. I'm going to move from source to destination, and then I'm going to move back. So you did source to auxiliary to destination. Now I'm going to do auxiliary to destination to source. So I'm going to rotate how we're doing this, because you got source, auxiliary, So it started off with what? Breaking it down, and went source to auxiliary to destination. So I'm going to move from source to destination. So I'm going to call it, if we just go back up here to 2, auxiliary, not move to destination. So it's going to start off being move to auxiliary and then auxiliary to destination. So it ends up being at least from a algorithm standpoint, it's relatively easy to understand, but not necessarily. If you try to write this in an iterative format, go for it. I think a lot of people have tried. So, and then here's the number of calls, how they were moved. So hopefully it gives you a rough idea what recursion is. You're going to get a few examples in practice, but in algorithms you're going to find sometimes this operation of calling itself to solve a problem is a good thing. Makes the algorithm easy to understand. In some cases, can be faster and keep lower storage, and that's just some of the questions you're asking yourself as we go through this. So as we solve and look at other data structures throughout the course of this semester, you're going to find benefits for using recursion versus an iterative format. So hopefully this helps. If anything else that confused you, you know how to get a hold of me. Talk to you later. Bye-bye.